So now we're going to look at our third case of trying to apply finite state methods to analyze the syntax of English, and we're going to look at object extracted relative clauses. To explain what those are and to get us going on this, I've given you an example. The rock that the squirrel likes can be found in the garden. So that's a sentence of English that probably feels pretty reasonable. Intuitively, it combines these two sentences in the right way. One sentence is the squirrel likes the rock, and the other is the rock can be found in the garden. And it involves a particular syntactic construction which we call relativization. So I'm going to start with this sentence in which the relativization occurs. The rock can be found in the garden. It's sort of a starting point. The relativization construction starts with the squirrel likes the rock, and we can think of the object of that clause, the rock, as being what's called extracted. So it doesn't appear in the position that it would ordinarily appear in an independent sentence. Rather, it's as if the word rock were somehow before the whole clause, and the word that introduces the body of the clause. And you can see that that then intuitively, in some sense, matches the broader frame. We have a match of rock in the relativization construction and the word rock in the context sentence in which the relativization construction appears. And then if you put the two together, you are using the relative clause as a post modifier of the word rock, of the noun. So we get the overall sentence, the rock that the squirrel likes can be found in the garden. That's how this works. Now, we'll generalize this pattern as described above here. This is the generalized pattern, and I've just substituted parts of speech and phrases. So in particular, N for noun, NP for noun phrase, and V for verb. And notice that this can also be nested many times. The rock can be found in the garden. We started with that. We relativize one time, and we get the rock that the squirrel likes can be found in the garden. We could then take the word squirrel, it itself is a noun, and we can target with relativization, where the original sentence might be the dog chases the squirrel. We relativize that, and then we use that to the resulting relative clause to modify squirrel, and we get the rock that the squirrel that the dog chases likes can be found in the garden. And this already starts to sound weird, probably to you, but it's a perfectly reasonable application of the generalization that we came up with here on the top, which just describes the object extracted relative clause construction. We could even continue doing this again. We could target the word dog. We could get something like, the rock that the squirrel that the dog that the woman owns chases likes can be found in the garden. Now, obviously, these resulting sentences get very, very hard to understand. But I'd like you to bear with me and take it on faith for the moment that it's theoretically productive to assume that they are implied by the relativization construction and thus are part of the language that we're trying to describe. And this connects to a classic distinction in the cognitive science of language, which is the relationship between competence and performance. At a high level, competence is our knowledge of language, performance is our ability to deploy that knowledge of language. So while these examples may tax human linguistic performance, it may be hard in the moment to put all the pieces together, keep track who's doing what to who, but at least provisionally, let's go with the idea that they should be a part of the theory of human grammatical competence. So let's talk about these examples. So I'm going to generalize these using N's and V's further. So now we're abstracting away from particular sentences, and I'm just going to use N's and V's inside the relative clauses. And before I go on, I'd like to recommend that you think about how you would try to capture this pattern, at least in part, with a finite state model. Just think about how you would try to do it. Okay, so go ahead and take a moment to do that, as long as you want. You can pause the video. Okay, I'll assume you're back. It turns out that this pattern cannot be modeled with finite state machines. And if you tried this exercise, you probably either found it implausible that you might be able to do this, or got frustrated, or thought you came up with a solution. It'll turn out that if you did come up with what you thought was a solution, it wouldn't be right. And we're going to go on to describe and show how this cannot be modeled with finite state machines, but showing it rigorously requires additional technical apparatus that we're going to cover next. And I want to point out that it's one thing to try and fail to come up with a finite state characterization of this pattern, it's another thing to show that such a characterization is impossible. It will turn out we are able to show that this characterization would be impossible with a finite state model, and that's what I'm going to get to next, is how to do that. So in order to understand how to do this, I have to introduce a new concept, which is the notion of pumping strings. So let's start with this finite state automaton that I've illustrated here. And this corresponds to the following regular expression. So this is relatively simple automaton and regular expression. Here is the following strings set that is accepted. So for example, dogs and cats, you can see quite easily is accepted through the automaton. Dogs and loads of cats is also accepted. And then I can also use this loop. Likewise, I could use this in the regular expression. I could use this and load star to repeat and loads as much as I want. So I could say, for example, dogs and loads of cats. And I could circle around here as many times as I want. So if I keep on doing this, I'd get more and more end loads. Okay, so there's an infinite sequence of strings of increasing length that have more and more instances of its loads in. So that these sentences obviously follow a pretty understandable pattern. And I want to note that I'll call that third sentence in the sequence S3. And I want you to focus on this end loads. I could repeat that substring in place as many times as I wanted. I could delete it, and I would wind up with something that is another sentence in this series, dogs and loads of cats. I could repeat it, dogs and loads of cats, and I would wind up with a sentence which is the next sentence in the sequence, and so forth. So I could repeat it 0 times, 1 time, 2 times, any time, many times as I want. That is called pumping the string with the substring end loads. Okay, and the pumping lemma informally says that in order for a language to be regular, it has to have the following property. Every string that is long enough in some sense has to have some non-empty intermediate section that can be arbitrarily pumped. That is, you can use it as few or as many times as you want without leaving the language. And in a finite state automaton or in a regular language, that notion of a repeatable intermediate section is actually quite manifest. So in a finite state automaton, it's a loop. So this loop you can use 0 times, 1 times, 2 times, as many times as you want. In a regular expression, it's a cleany star. Okay, so the informal statement is that if you're able to expand to arbitrarily long strings, then you have to have a repeatable section like that. Here's the formal statement. Suppose that a language is regular. There must be some integer k such that for every string that is longer than k, you can decompose or write the string into 3 components, x, y, and z. So S, the string will be the concatenation of x and y and z. X, y, and z are substrings. Those individual pieces don't necessarily have to be an L, but their concatenation has to be an L. X, y, z has to be an L. And the following criteria must hold. First of all, the intermediate part, y, has to be non-empty. It has to have length at least 1. Second, the length of x and y together has to be less than or equal to the integer k that we fixed. So note that you have to fix that integer's value for the entire language, but you have to be able to find this decomposition for every string in the language above that length k. And the third criterion is that y has to be pumpable in the string x, y, z. You have to be able to repeat y 0 or more times. So since y is non-empty, one of those, the 0 times repetition, leads to a string that is shorter than s. If you have y exactly once, you would have s. If you have y more than once, you'll have a string that is longer than s. And that infinite series of strings that derives from pumping y in s all has to be an L. Okay, so here's an example of the pumping lemma's successful application on a regular language. So we'll take this regular language, alternatively characterizable by the finite state automaton or by the regular expression, and we're going to show that the pumping lemma, which I have in the upper left, repeated, is satisfied. So let me just arbitrarily choose an integer that's reasonably high. It's 6. K is going to be 6. In this particular example, if I choose k to be too small, this is not going to work. But if I have a reasonably high value of k, it's going to work. And I encourage you to try this afterwards on your own to see what's the threshold value of k, for which if you go below it, then you won't be able to do this. But it's okay because the pumping lemma simply requires that we choose, and there's some k that we can choose. And so 6 is fine. If it works, it works. So we now need to analyze, we need to check whether this property for every string, everything that follows that in the pumping lemma application, holds for every string that is of length greater than 6. So let's start with the shortest possible string that is of length greater than 6, which is this string, dogs and loads of cats. And the decomposition, I need to find a decomposition into x, y, z. And I'm going to use this decomposition, where x is dogs and loads, y is and loads, and z is of cats. Okay, so let's see whether each of the 3 criteria that we have up in the pumping lemma hold. First of all, is y non-empty? Yes. Y is of length 2, so it's non-empty. So we've checked our first criterion. Is the length of the concatenation of x and y less than or equal to k? The answer is yes. So the length of x and y together is 5, k is 6. So that's checked. Now what about the last one? For all I greater than or equal to 0, is x, y to the I, z in the language? Can y be pumped in x, y, z? And the answer is yes. So if we omitted it, we would have dogs and loads of cats, which is manifestly accepted. And because of the loop, you can just tell that if I used y over and over again, it would be fine because it would just match with this part of the loop. Okay, so that's the successful application of the pumping lemma. And now that was only one string. We actually have to show that for any infinite set of strings, for any of the infinite set of strings of length greater than 6. However, it should be very clear to you that in this case, any such string will have the form of additional and loads components in it in what can be understood to be this position. And so the decomposition that I would use if I have more and loads that appear here is that I would put those and loads parts into z. I would put them in the prefix before of cats. So if I had dogs and loads and loads and loads of cats, I would make x dogs and loads, y and loads, and z and loads of cats. And all of the same criteria would hold. Z would have gotten longer, but x and y would have stayed the same, and all of the criteria would still continue to hold. So the pumping lemma is satisfied for this language, and the language is regular. So now that we've set the stage that way, we're in a position to make the argument that English is not regular. And this is the process by which we're going to do it. First of all, we can't talk about English without, in a formal language theory setting, without defining the idealization of the natural language that we're interested in from a formal language theoretic perspective. What is the set of strings we're talking about? I'm actually going to hedge a little bit on exactly what that set is, because I think it's hard to say exactly what it is, but let's just assume it exists, and we'll call it English in small caps. And now I will define a regular expression that defines a regular language. We'll call it L double dagger, and we'll call its intersection with English, with that idealization of English, L dagger. So L dagger is the intersection of English and L double dagger. Okay. Now, if English is regular, then L dagger must be regular because regular languages are closed under intersection. That is a crucial property here. We will use the pumping lemma, however, to show that L dagger is not regular. Okay, so we're going to get to this language, L dagger, and we're going to show that it's not regular, but it would have had to be regular in order for English to be regular. So this will show that English is not regular. That is our formal idealization of English. Okay, so how are we going to do this? The infinite set that we're going to get to, based on this generalization of multiple center embedded object relative clauses, is what we see above. It's the infinite set, we'll call it L dagger, and we're going to summarize it, this infinite series, as follows. I'm just going to call it the rock, and then I'll have this that the n to the I, v to the I can be found in the garden. And we haven't introduced that formal notation yet, but to explain what I mean by that, for any I greater than or equal to 0, it has to be the case that the number of that the n repetitions that occurs here is the same as the number of v repetitions that occurs here. They have to appear in that position and consecutively with each other. So that is all the that the n's would occur before any of the v's occur. That has to happen the same number of times as each other. So the number of that the n's has to match the number of v's. Now, note that strings of the following form are not okay English. The rock that the n to the I, v to the j can be found in the garden when I and j are not equal to each other. So for example, let's say j is equal to 0 and I is equal to 1. I would have something like the rock that the squirrel can be found in the garden. That's clearly not English. It's missing a verb. Okay. And that's going to be important. So we are going to assume, and this is important, we're going to assume that L dagger is part, formally, that it is a subset of the formal idealization that we call English. It's clearly not all of English. And that's important because we're not going to be able to analyze all of English, but we are going to be able to analyze L dagger. And so if we can get from that formal language idealization English to L dagger, we can maybe do something with L dagger. That's the strategy that we're taking. Okay, so we have this L dagger. So how do we get to that? Let's look at this regular language defined by the following regular expression. We're going to call this L double dagger. This is the rock that the end star, V star, can be found in the garden. So these are each the Kleene star. So there's no requirement here that the number of the ends and the number of V's match each other with this regular language. This is an infinite set of strings, but there's no matching requirement. Then, clearly from what I showed you on the previous slide, the formal idealization of English intersected with this regular language is L dagger, which we have up on the top. We know that because we assumed that L dagger is a subset of English, and that other cases of the rock that the end of the I, V to the J can be found in the garden, where I and J were not equal, are not part of English. Those things together allow us to intersect the formal idealization of English with this example, and we get out L dagger, which is what we wanted to be working with. Okay. Now, how do we use this? So remember that English, and we don't know the status of English, we know that L double dagger is regular. We can see that because there's a regular expression that defines it. Okay, so if it is the case that English is regular, then that implies that L dagger must be regular. So that is one thing we can use. We're going to be interested in the contrapositive. So we know that once again that L double dagger is regular. Let's imagine that L dagger is not regular. That must imply that English is not regular. So that's the contrapositive. If L dagger is not regular, then English can't be regular either. That's the contrapositive of the closure under intersection of regular languages as we're applying it here. And we're going to be able to use the pumping lemma for regular languages to show that L dagger is not regular. So how do we do that? Once again, at the top, I have the pumping lemma for regular languages. Let's prove that L dagger is not regular by contradiction. So if L dagger were regular, then there must be some K, according to the pumping lemma condition up here, such that everything that follows in the pumping lemma statement here applies. This holds true. So in order to prove that L dagger is not regular by contradiction, all I need to do is to say, what I need to do is I need to say that no matter what K is chosen, I will not be able to analyze every string in L in a way that the pumping lemma says I should be able to. So I don't get to choose my K. I have to imagine that somebody is adversarially choosing a K for me, and they're trying to prove the pumping lemma that the pumping lemma holds, and I have to show that no matter what K is chosen, there's going to be some string that I'm not going to be able to get all the pumping lemma conditions hold. So I'm going to choose the following string. Suppose there's some such K. I'm just going to choose the string, the rock that the end of the K, V to the K, can be found in the garden. Clearly, this is of length greater than K, so the pumping lemma requirements should hold. But now let's see. If they held, I would be able to find an appropriate XYZ decomposition according to the above. Now, let's think about this for a moment. So let's start with what Y contains. So because the length of X and Y together is less than K, Y cannot contain any V's. Because XY cannot reach, XY sort of has to, at most, it can go somewhere in here. Because this length is 3k plus 2. And xy is less than length k. So y cannot contain any v's. So now let's distinguish two cases. So it's possible that there's at least one n in y. You'll notice that in this case, the fifth symbol in the string is going to be an n. So if n is long enough, there's plenty of room for reasonable values, many values of k, for y to include some n's. If y includes one or more n's, then pumping y would yield a string that doesn't have the same number of n's and v's. So if we took y to the 0, then we have one less n than we have v's. If we took y to the greater than 1, we would have more n's than v's. So this would take us out of L-dagger, because L-dagger requires that the numbers of n's and v's are the same. Alternatively, y might not have any n's in it. If it doesn't, then it has to be the string the, that, or that the. And I think that you can see that no matter what that is, no matter what option we choose, y could not be pumpable. So for example, if it's the, then pumping it would lead to sequences of multiple thes in a row. And there's no multiple thes in a row that are possible in this language. Likewise with the word that, and with that the, same thing. There are no multiple that thes in a row. So y couldn't be pumpable if it has n's, y couldn't be pumpable if it doesn't have n's. Either way, we're going to wind up with a contradiction. For the formal abstraction of English to be regular, L-dagger would have had to be regular, but L-dagger can't be regular according to the pumping lemma. And so our assumption that L-dagger were regular has fallen apart, and we have that L-dagger isn't regular. And as a result, English isn't regular either. So this shows that if you take the formal abstraction of the infinite series of relative clause cases that I showed you to be a reasonable set of things to have in the idealization of English that we want to model, we are not going to be able to do that with regular languages. So to summarize, we've seen three syntactic phenomena in English. We looked at a very relatively simple case of a gerund adjective ambiguity. We saw another case of NPs with stacked prepositional phrase post modifiers. In both of those cases, we were interested not just in the weak generative capacity, but the strong generative capacity. Are there structural descriptions that we could assign to the strings that we were interested in? And what we found is that for the gerund adjective ambiguity, finite state models could do both the weak generative capacity problem, model all the strings, which strings are and aren't accepted, and it could also do the strong generative capacity component of assigning structural descriptions. The second thing that we looked at is noun phrases with stacked prepositional phrase post modifiers, and that was interesting because we found that the weak generative capacity of finite state machines was sufficient. However, the strong generative capacity was not. And the reason is that there are more ways of words associating with each other that get multiplied out together as you stack more prepositional phrase post modifiers than the finite state framework allows us to track. And the last example is one where we didn't actually have to go even bother with strong generative capacity because finite state models failed on weak generative capacity as well. This is multiply nested object relative clauses. So, bumping up a bit, both weak and strong generative capacity of grammatical formalisms are of interest. Weak is like, does your model actually predict what is and isn't in English in terms of word sequences? What word sequences do and don't constitute legitimate English? Strong generative capacity is about something additional. It's about, am I describing the strings that are in the language in ways that corresponds to kind of descriptions that I want? And in order to evaluate whether that's appropriate, you have to bring in additional theoretical apparatus, additional desiderata, and we were fairly informal about what that really is. But you notice that it already starts to get at certain aspects of meaning, especially insofar as they relate to syntax. And we're going to get to that more and more as we go forward in future weeks. We also found that finite state models, while they can capture some of the features of English syntactic structure, they don't have the strong or the weak generative capacity for other features. So we know that finite state models are already out as candidates of a comprehensive, satisfactory account of English syntax. Looking ahead, now these are classic results. So these results actually date back over 50 years, but I think they're still of great relevance because they provide insight into what finite state models can do, which is a lot, but also what they can't do. And it sets the stage and helps you understand why the kind of theoretical apparatus that you see in linguistics is relevant and continues to be relevant for the study of language. And these results motivate grammatical formalisms that have been central to cognitive science of language for decades and that we're going to look at next. Thanks.